Hi, Mr. Richards here. Today's lesson is on theoretical and experimental probability. What you'll learn is about theoretical and experimental probability, and let's start with the definitions of those. For theoretical probability, this is what should happen when conducting a probability experiment As for experimental probability, this is what actually happens when conducting a probability experiment. And the easy example for right now deals with flipping a coin. And you should get heads half the time. You know, there's heads or tails, and heads are one of the two outcomes, so 1/2 would be the theoretical probability. But if you flip a coin, say 5 times, and get heads 4 out of the 5 times, then that would be an experimental probability of 4/5. So, you know, there is going to be a difference between theoretical, what should happen, and experimental, what actually happens. So let's get into our real-world link with carnival games. The prize wheels for a carnival game are shown. You receive a less expensive prize if you spin and win on wheel A. You receive a more expensive prize if you spin and win on wheel B. In a uniform probability model, each outcome has an equal probability of happening. So when you look at the two wheels and compare which wheel has a uniform probability, well, here it looks like everything is divided into 4 equal parts for wheel A, versus wheel B, where your losing sections look to be a little bit larger than your winning sections. So which wheel has a uniform probability? I would argue that this would be wheel A. Now I went ahead and spun a paperclip on each of these wheels, and here were my results. When I spun on wheel A, I had a win, a loss, a win, and I got lucky and won the 4th time. Compared to wheel B, I lost, I lost, I lost, but I came through in the 4th time and won. Now, why do you think winners on wheel A will receive a less expensive prize than winners on wheel B? Well, you have a higher probability of winning on wheel A. You have, it looks like, a 50% chance of winning in theory on wheel A, whereas you have much less than that on wheel B. So winning would be much more difficult, so you could get a more expensive prize. So to summarize all of that, we could say something like, there is a better chance of winning on wheel A. Theoretical probability is based on uniform probability, what should happen when conducting a probability experiment. Experimental probability is based on relative frequency, what actually occurs during such an experiment. The theoretical probability and the experimental probability of an event may or may not be the same. As the number of attempts increases, the theoretical probability and the experimental probability should be closer in value. Again, if we go back to our coin flipping example, what should happen? You should get a heads 1 out of 2 times, 50% of the time. And if you just flip it 3 times and get 2 heads and 1 tail, you would think, well, that's 2/3. But the more you flip that coin, say you flip it 100 times, you should get a bit closer to 50 heads and 50 tails. If you flipped it 1,000 times, the more you conduct an experiment, you should get closer to the theoretical probability. In our guided examples, the graph shows the results of an experiment in which a spinner with 3 equal sections is spun 60 times. Find the experimental probability of spinning red for this experiment. The graph indicates that the spinner landed on red 24 times, blue 15 times, and green 21 times. So the probability of getting a red here is the number of times the reds occurred over the total number of spins. Well, it was spun 60 times, and the red occurred 24 times, and if we simplify 24 over 60, that is 2/5. Now, as we look down to a guided example 2, compare the experimental probability you found in example 1 to its theoretical probability. Well, there's 3 equal sections on this spinner: green, blue, red. In theory, the probability of getting a red is 1 out of 3, as that's indicated here by the 1/3. Now, 2/5, it's saying, is about 1/3. So the experimental probability is close to the theoretical probability. However, I would argue that we can go into even more detail here. I think, and I know, that 2/5 is greater than 1/3. I mean, if you were to get these into decimals, 2/5 is 4/10, and 1/3 is that 0.3 or 3 repeating. And so you could even make the argument here that the experimental probability is greater than the theoretical probability. And if you were to make that argument, I would agree. So let's see if we got it. Refer to example 1. If the spinner was spun 3 more times and landed on green each time, find the experimental probability of spinning green for this experiment. Well, if we start our work up here near the top for A, let's write down what our new results would be. For green, this would have occurred now 3 more times, so 24 times. Blue was still at 15, and red is still at 24, which gets us a total now. We had 60. We added 3 more spins, so our total spins now is 63. So find the experimental probability of spinning green. Well, that's going to be the number of times that the green occurred over the total, which here is 24 over 63. And believe it or not, you can divide by 3 on top and bottom. We should all recognize that 24 can be divided by 3 to get 8. But for the 63, remember your divisibility rule for 3. If you can add the digits of a number, 6 plus 3 is 9, and that sum is divisible by 3. Well, 9 is divisible by 3. Then that means 63 is also divisible by 3. And 63 divided by 3 is 21. So 8/21 is our experimental probability of getting a green. In part B, compare the experimental probability you found in exercise A to its theoretical probability. Well, let's break down 8/21 and 1/3. Again, 1/3 is going to be the theoretical probability. I don't want to gloss over that. 1/3 is the theoretical probability because there are 3 equal sections, and the probability of landing on green is 1 out of those 3. So again, it's 1/3, like red was 1/3 above. If we were to look at these as decimals, 1/3 is again, the 0.3 repeating. The 8/21st, if you were to either long divide or just in a calculator, 8 divided by 21, is 0.38, and it kind of keeps going, 0.9 and so forth. And so this one, I would actually be okay with you saying that, well, 8/21 is very similar to 1/3. It's about equal to 1/3. And so if you wanted to say that the experimental probability is close to the theoretical probability, I would be okay with that. Or if you wanted to even go more detailed, since 0.38 ... is a little bit bigger than 0.333, I would be okay with someone making the argument that the experimental probability is greater than the theoretical probability, even though it's just by a little bit. So either it's close, that's acceptable, or if you wanted to go in really fine detail and say, yes, the experimental probability is greater than the theoretical probability, you could do that as well. In our third and fourth guided examples, example 3, 2 number cubes are rolled together 20 times. A sum of 9 is rolled 8 times. What is the experimental probability of rolling a sum of 9? Well, it's rolled 8 times out of 20, so it's 8/20, so it simplifies to 2/5. Guided example 4. Compare the experimental probability you found in example 3 to its theoretical probability. If the probabilities are not close, explain a possible reason for the discrepancy. When rolling 2 number cubes, there are 36 possible outcomes. Now, how do we know that? Well, how many outcomes do we have for the first number cube? We have 6 possible outcomes for the first number cube, 1, 2, 3, 4, 5, and 6. How many different outcomes do we have for the second number cube? Well, another 6. So to find the total number of outcomes when you're running 2 different things, this would be 6 times 6, which is 36. This is what's called the fundamental counting principle, which is something we'll be talking about later in this chapter. You could also list out, well, I can get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, and so on to get your 36 possible outcomes. But yeah, I wouldn't do that right now. For now, let's just kind of think about the fundamental counting principle, which we'll get to later in the chapter. There's 6 possible outcomes for the first dice, 6 possible outcomes for the second. 6 times 6 is 36. So there's 36 possible outcomes. Now, the theoretical probability of rolling a sum of 9, it says, is 4/36, which is 1/9. And how do we get to that? Well, think about the different ways you can get to a 9 when you roll 2 number cubes, 2 dice. You can get a 3 and a 6, a 4 and a 5 and a 4, and a 6 and a 3. I mean, those are all possibilities for getting to a sum of 9. So that's 4/36, which is 1/9. Since 1/9 is not close to 2/5, the experimental probability is not close to the theoretical probability. I mean, if you wanted to look and compare these as decimals, once again, 1/9 is the 0.1 repeating. 2/5 is 0.4 or 4/10, so those are nowhere close. So the experimental probability was much higher than the theoretical probability. One possible explanation is that there were not enough trials, which is true. There's only 20 times where the dice were rolled, and so maybe that's not enough to get a true good experimental probability. Let's continue on to our got it questions. In example 3, what is the experimental probability of rolling a sum that is not 9? Well, they rolled a sum of 9 8 times out of 20. What's left in example C here? Well, 12. 12 times it did not come up as a 9, so 12 out of 20 would be the probability of not rolling a 9. We can simplify that down by dividing by 4 on top and bottom to 3/5. So for C, we can write 3/5. Example D. 2 coins are tossed 10 times. Both coins land on heads 6 times. Compare the experimental probability to the theoretical probability. If the probabilities are not close, explain a possible reason for the discrepancy. Well, let's look into the experimental probability first. And I'll just abbreviate that as EP. Both coins land on heads 6 times. So that would mean that 6 out of 10 times the coins landed on heads. And to simplify that down then, this would be equal to 3/5. Now what about the TP? Not toilet paper, but theoretical probability. This is when we now need to look at how many possible outcomes are there when we flip 2 coins. Now, you may have done tree diagrams in the past. You could get on the first time a heads or a tail. And if you get a heads on the first one, you could go heads, tails on the second flip. And if you got a tails the first time, you could still go heads or tails for the second. And so you could go heads, 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 tails, tails, heads, tails, tails when you flip 2 coins. So what's the theoretical probability of getting 2 heads? Well, that would just be 1 out of the 4. So our experimental probability for this experiment was 3/5. The theoretical probability for this was 1/4. And so for this, very similar to what the guided examples were, we can say 3/5 is not close to 1/4. One possible explanation is that there were not enough trials, meaning only tossing it 10 times may not provide the best and most accurate results for what should be happening. Let's move on to D. Suppose 3 coins are tossed 10 times. All 3 coins land on heads 1 time. Compare the experimental probability to the theoretical probability. If the probabilities are not close, explain a possible reason for the discrepancy. All right, we can do this. Let's look at the experimental probability first. EP. All 3 coins landed on heads 1 time. So this was just a 1 out of 10. All right, simple enough. Now what about our TP? Well, if we really break this down again, and I'm going to do this over here on the left side here, what are our options the first coin flip? You could get heads, or you could get tails. What about the second coin flip as we try to make a tree diagram here? You could get heads or tails. And then again, if you had tails the first time, you could get heads or tails on the second time. So this is the first flip. This is the second flip. And if we were to have a third flip, you could go heads, tails, heads, tails, heads, tails, heads, tails. So you could go heads, 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 tails, heads, tails, heads, heads, tails, 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 head, head, tails, head, tail, 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 head, tail, tail, tail. Those are the 8 possible outcomes when you flip 3 coins in theory. What then is the probability of all 3 coins landing on heads? Well, that would be this track here, our heads, 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 which is just 1 out of the 8. So the theoretical probability is going to be 1/8. Well, if we look at 1/10 as a decimal, that's 0.1. And if we look at 1/8 as a decimal, that's 0.125. And for the sake of this question, those are close. So we can say, well, 1/10 is close to 1/8. So this time, even though we still had 10 trials, they were pretty close to the experimental and theoretical probabilities. Now we can also use probabilities, theoretical and experimental, to make predictions about future events. In our 5th and last guided example, a DVD store sold 670 action DVDs, 580 comedy DVDs, 450 drama DVDs, and 300 horror DVDs. If a media buyer expects to sell 5,000 DVDs this year, based on these results, how many comedy DVDs should she buy, and explain? Well, if we look, last year 2,000 DVDs were sold. We added the 670, the 580, 450, and the 300 to get the 2,000. So 580 of those were comedy, so 580 over 2,000, which simplifies to 29 over 100. Now what we're doing here is setting up a proportion, saying, all right, 29 over 100 is going to equal the x, where the x is my unknown. The x are the number of comedy DVDs I should buy this year out of the 5,000 that are going to be sold. Well, if you cross multiply 29 times 5,000, 100 times x, and solve, you'll get 1,450 comedy DVDs. Now let's twist this. Let's say that we want to find out how many, let's go with drama. How many drama DVDs should the same person buy? Well, once again, there were a total of 2,000 DVDs sold last year. Of those, 450 were drama. So we can start off by saying, all right, 450 over 2,000. And it will be easier if we can figure out a way to simplify these, and there is. You can divide both our top and bottom here by 50, which simplifies this down to 9 out of 40. So 9 out of 40 DVDs, if we simplify this word, drama DVDs, sold last year. Now, let's set up a proportion. 9 over 40 is going to be equal to, there are 5,000 predicted for the future. And so that's going to go on the bottom. And then our unknown x are the number of drama DVDs she should be buying. So if we cross multiply this now, 9 times 5,000 is going to equal 40 times x. 9 times 5,000 is 45,000 equals 40x. And if you divide by 40 on both sides, our answer is 1,125 DVDs equals x. And that is it for this lesson on theoretical and experimental probability. Good luck.